I'm going to focus on a variation of the example that's on page 202 in the textbook. The textbook looks at the case where an airplane is making a loop in the vertical direction and the airplane is at the top of its arc. I want to look at the case where the airplane is partway up and try to figure out what is the force exerted on a passenger by their seat at this point. So the angle here between vertical and the perpendicular to the plane's path at that point is 45 degrees. So I've set the problem up here, and I've chosen my passenger as the system. Then the earth and the seat are the only two things that are actually in the surroundings, and that gives me my free body diagram here. Now, the net force is along that line towards the center of the circle. Now, I'm assuming that V is constant, at least for some short period of the arc, right around the point that we're interested in. So the magnitude of the velocity is not changing. So I'm assuming that the magnitude of V, the speed, is constant. So that means then that the net force has to be along that line pointing towards the center. And just based on the fact that these two forces have to add up to be equal to this, that lets me know that the normal force isn't actually going to be along that line. So not only is the seat, the bottom of the seat pushing, but the back of the seat is also going to be pushing on the passenger a little bit. So here's my strategy. The first thing I'm going to do is figure out what does the net force need to be in order for this plane to be going in a circle. And then I can write out an equation for net force in terms of this. Then I'm going to write the vector forces in terms of the variables, both the normal force and the gravitational force, and then set those two equations for F net equal to one another to see if I can find the normal force. And in the end, I should be able to find an angle for this force up here. Okay, so what does that net force need to be? Well, I'm assuming that V is much, much less than C, so that gamma is approximately 1. That means that the magnitude of the net force, is just going to be approximately equal to mv squared over r. Now, I need to actually figure out the direction of that force. So I said it has to be directed towards the center of the circle, and we know that direction. So I'm going to set up my coordinate system at the center of the circle. So there's my x-axis, there's my y-axis, and so this represents the line going from the center of the circle down to the airplane. And that's also the direction of the force that the net force needs to be. So this angle right here is 45 degrees. So I can figure out what the unit vector for this force needs to be. It's going to be, and actually this force should actually be up like this. Ignore this. So this angle is 45 degrees. So my equation for the net force then is approximately mv squared over r. And then my angle between this vector and the x-axis is going to be 45 plus 90, or 135. My angle with respect to the y-axis is just 45. My angle with respect to the z-axis is 90. Cosine of 90 is 0. So there's my net force based on the fact that this thing's moving in a circle. The next thing I need to do is write down equations for my force. Let's start off with F grav, which is really easy. The gravitational force is just going to be mg times 0 minus 1, 0. Just a reminder, these two zeros are coming from the fact that there's a 90-degree angle between the x-axis and a vector straight down. This minus 1 comes from the fact that if we have a vector straight down, the angle between the positive y-axis and that vector is 180. The cosine of 180 is negative 1. F norm is equal to F norm, and So let me redraw these here, x and y. So this is going to be at some angle, and let's call that angle theta. And this angle here will be 90 plus theta. So we have cosine of 90 plus theta, comma, cosine of theta, comma, 0. So adding these two together will give me a second equation for the net force. F net is equal to F norm cosine of 90 plus theta, comma, F norm cos theta minus mg, comma, 0. All right, so I have two equations for the net force. The first one coming from what the centripetal force needs to be to keep this moving in the circle. This one coming from the free body diagram. Those two have to be equal with one another. So what we can do is just compare the terms. So the x terms, I'm going to have mv squared over r times cos 135 is equal to f norm cos 90 plus theta. The y components give me mv squared over r cos 45 is equal to f norm cos theta minus mg. So one thing that I know is that the cosine of 90 plus theta will give me minus sine. So that's going to allow me to simplify things a little bit. One thing I'm going to do is get f norm and the either cosine or sine on one side of the equation by itself. So this equation, when I make that substitution for minus sine, I get that f norm sine theta is equal to minus mv squared over r cos 135. If I add mg to both sides of this equation, I get f norm cosine theta is equal to mg plus mv squared over r cos 45. And what I'm going to do is take the ratio of these two equations, and that's going to give me the tangent of theta. So the ratio of these two equations will end up being f norm sine theta over f norm cosine theta equals minus mv squared over r cos 135 all over mg plus mv squared over r cos 45. And these two f norms will cancel out, and this just becomes a tangent theta. And so I could now solve for that unknown angle of the normal force on the passenger by the seat. So let's go ahead and just write that equation out. Tangent of theta is equal to negative mv squared over r cos 135 divided by mg plus mv squared over r cos 45. Cos 45. All right. The second thing to solve for then is the normal force magnitude, and I can get that from these equations, solve for theta, and then plug things in. The algebra actually gets to be a little bit sticky, and so I'm not going to plow through that. But what I wanted you to see is just how to set these things up and how to go through and solve for some of the different quantities involved. So this is what we get for our angle. All right, one other thing I want to talk about in this section is the feeling of acceleration. And our body tends to lie to us. In fact, if you pay attention, the way our body thinks a force is, usually is exactly opposite the direction that that force acts. So if you imagine yourself sitting in a car that's turning to the right, just think of a second, which way does your body feel like it's being pushed? What you'll find is that you feel like the force is outside, but based on your physics knowledge, you know that that force actually has to be towards the inside of the turn. Think of another example. Imagine that you are in an elevator, and that elevator suddenly starts to drop, like right at the start of the motion. What you feel is it feels like you kind of become a little weightless, or you feel like you kind of don't feel the force of the floor anymore. But what you know is that you have to be accelerating downward, so there has to be a net force down. Most any situation where you actually feel a force with your body, you'll find that what you're feeling is actually opposite the direction of the actual force. We call this the apparent weight. It's not actually a force, but it's just what our body is feeling. So if you imagine yourself in a car that's accelerating, you have your normal weight, and then as the car accelerates, you feel like you're accelerating backward. And so if you combine that feeling with the weight, it kind of feels like you're being pushed back and down into the seat. What's actually happening is that you're accelerating in the forward direction. Another good example of your senses kind of lying to you is when you're in orbit on the space station or something like that. It turns out that the gravitational force on your body in orbit is only about 90% of mg. Mg is that gravitational force you feel on the surface of the Earth. So the Earth is only pulling about 10% less than it does when you're on the surface of the Earth when you're in orbit. But what's happening is the space station is falling along with you. This is essentially what we call free fall. And so you're not actually feeling any of these surfaces pushing on you. So here's the space station that you're standing in, and you're both moving with a velocity in this direction, and you're both experiencing a force in this direction. And so you're falling together, and you're actually falling at a rate that's equivalent to the acceleration you get at about 90% of g. A third example of this apparent force is sometimes in the movies you will see circular space stations that are rotating, and they generate a artificial gravity, they sometimes call it. And that's really not the case. It's not that there's any sort of additional force, but what's happening is if this space station is spinning fast enough, you will feel like you are being pushed outward and up against the wall or the floors. But in fact, that's not the case. So take a look at the section dealing with the feeling of force and make sure you understand what's actually going on here.